Now let's move on to the second category of rendering resources, mesh data. When we analyze mesh memory cost, the main influencing factors are vertex count, read-write-write vertex attributes, skeleton-related data, additional vertex channels. The test environment remains the same. The device used was an Oppo R17, a mid to low tier mobile device. The engine version was Unity 2022.3. The test asset was an open source monster model. The model itself was not highly complex, but it contained multiple vertex attributes. These included blend weight information, blend index data, basic skeletal animation metadata. Let's first look at the read-write setting. When read-write is enabled, we observe a slight increase in both runtime cost and package size. But the most interesting observation is memory behavior. Here is where meshes behave very differently from textures. For textures, memory scaling is very clear. For example, memory may increase from 1 megabyte to 2 megabytes, but for meshes, the memory increase is surprisingly small. Let's compare numbers. Under default runtime conditions, mesh memory usage was about 1.139 megabytes. If we inspect mesh memory inside the inspector, you might expect a larger footprint, because the inspector calculates vertex positions, skinning information, additional mesh attributes. And if read-write truly duplicated everything, mesh memory should roughly double. But in practice, that is not what we observed. This happens because Unity's mesh resource definition is more complex than texture resources. Most mesh assets are imported through FBX pipelines. During import, mesh data is decomposed into multiple layers: base vertex geometry, animation skinning data, auxiliary attribute buffers. When read-write is enabled, only certain runtime accessible vertex buffers may be duplicated. Other data, such as skeletal information, is typically not affected. Therefore, in production optimization, we generally do not recommend enabling read-write for most mesh assets, unless your gameplay logic requires runtime vertex modification, because read-write does introduce extra overhead. Now let's look deeper into vertex attributes. It's important to understand something here. The experiment uses a representative sample model. Real project assets may differ. Skeleton complexity, vertex density, and animation structure can vary significantly. However, the experiment still clearly shows one pattern. Vertex metadata can dominate mesh memory cost, sometimes more than expected. For example, we tested bone weighting data. When bone weight information was absent, memory usage was about 0.171. When skeletal data was included, memory usage increased to 0.766 megabytes. Package size and loading time also showed noticeable differences. Next, let's talk about UV channels. We compared two scenarios: single UV channel, 4 UV channels. The difference was significant. A very common situation in production is this. Artists may generate models using tools like Blender or similar editors. During modeling, multiple vertex attributes may be embedded early, but in the final game pipeline, some of those attributes are never actually used, yet they may still be stored in the mesh. Many developers underestimate this impact. They may assume vertex metadata cost is negligible, but when asset scale increases, these hidden attributes accumulate, and the impact becomes measurable. Therefore, it is important to verify, does the shader pipeline actually use these vertex attributes? If a vertex channel is not used, consider removing it through post-processing scripts. We also tested other attributes: color channels, tangent vectors, normal vectors. These DNA-level mesh properties introduce additional storage overhead. The dataset we collected was large. Testing was conducted across multiple Unity versions, multiple hardware tiers. Due to time constraints, we cannot display all results today, but the general trend is clear. When performing mesh memory optimization, the key is not only vertex count, it is also attribute redundancy, pipeline usage validation, shader dependency analysis. That's why mesh optimization is often about pipeline correctness first and data reduction second.